introductions in her absence, and so I'm afraid I have to introduce myself this morning. But someone else can kick me off if I'm overrunning at 11. For anyone who doesn't know me already, I'm Sarah Jane Locke. I'm from the University of Leeds, and I'm going to talk about work today that I'm doing as part of the Gung-Ho project with the Met Office. I'm not really going to talk about the Gung-Ho project in any great detail, but just to say that it's a project that's being led by the Met Office to investigate methods for their next generation forecasting model. So at this stage it really is an investigation rather than writing a model to produce some new forecasts, with the idea that this new model would be in operation at the end of this decade, so kind of 2020, and therefore needs to be able to work on massively parallel computers. So my input to the project so far has been in looking at how explicit-based time-stepping methods might be able to help with that problem. And it's work that I've been doing with Nigel Wood and Andrew Staniforth at the Met Office and Hilary Weller, who you all know from Reading. Okay, so I'm going to start with a little story. Once upon a time, there is currently the Met Office's forecasting model, the unified model. And so I've tried to put together here some indication of the scales that are involved in their current forecasts. So this is old news to a lot of you, but hopefully it sets the scene. So in the current global weather forecasting model, they're working with a horizontal mesh spacing of about 25 kilometres. And so in the table here, I've got kind of orders of magnitude indicated for horizontal mesh spacings, vertical mesh spacings, kind of an indication of the sorts of speeds associated with some of the important processes in the atmosphere, and what I'm trying to indicate is the sort of time steps that you might anticipate requiring to resolve those processes. And so I've made a kind of assumption here that to really resolve a process you need a Courant number of around 1, and what that indicates is that even with their current model, for horizontally propagating modes, the time step associated with the horizontally propagating modes needs to be about 100 seconds. And then if you consider the vertical direction, the mesh spacing in the vertical is much smaller near the lower boundary, order a metre, and therefore to resolve those vertically propagating modes, you're looking at a time step that's around 0.01 seconds, so it's a stiff problem. And I've just noted that in practice, currently, the unified model achieves a time step that's about 1,000 seconds, so about 10 times that of the time step required to resolve horizontally propagating modes. And they do that by using a semi-implicit scheme, so thereby avoiding constraints on the time step associated with sound and gravity modes, and combined with a semi-Lagrangian approach, which avoids constraints from strong advection. So that's the current scene. And what we're looking at is what's likely to be happening in sort of 10 years' time. And by then, we might assume, in this new model, the Gung-Ho model, that the mesh spacing in the horizontal is more like a 1 kilometre mesh spacing, which would therefore require time steps of about 10 seconds to resolve the horizontally propagating modes. And so what we're immediately looking at is 10 times more time steps to get to the same forecast time. So there's already a big computational problem, and associated with that, we want to. So if we're going to move to a horizontal mesh spacing of 1 kilometre, that's a lot more nodes on the globe, and we can hope to make all those computations by using a much bigger computer. But we might be assuming, in order to do this computation just in 10 more times, so 10 more time steps, we might assume perfect scalability. For the UN, that's currently a dangerous assumption because of the methods that are currently being used. So as I said, they're using a semi-implicit method at the moment, and that requires global communications to solve the elliptic problem that results. They're also using a semi-Lagrangian approach, and that requires non-local, on-demand communications. So those are two bottlenecks that they've already identified with their current model, and so we're looking at potentially other methods that might help get around that problem. So focusing now on gung-ho. What are we looking at? So we can see that the major constraint is coming from the vertical motions because of this mesh spacing being so much smaller. So we've got mesh spacings in the horizontal of 1 kilometre, and in the vertical ranging from about 1 metre up to 1 kilometre. And so you can see that the time steps that we're having to consider to really resolve those flows are much, much smaller. And so we've already identified that in the current model they're getting around this problem by using an implicit scheme for the fast modes. Well, we could consider just using the implicit scheme for just the vertical fast modes, so sound and gravity, and also vertical advection, which is still requiring a time step much smaller than the time steps associated with the horizontal motions. In addition, or as well, we could also continue to consider a semi-Lagrangian approach for advection terms, and this is really appealing to the Met Office. They like their semi-Lagrangian approach for stability, but also for the consistency that it brings to their advection computations. So Andrew Staniforth keeps talking to me about how if we use an implicit approach for the vertical advection to get around this constraint here, while using an explicit approach for the horizontal advection, the damping and deceleration that comes from using implicit schemes at high Courant numbers is likely to destroy the baroclinic instability development in a model and lead to storms propagating too slowly across the North Atlantic, which is important for UK weather. So, so they're really keen to be able to keep hold of a semi-Lagrangian approach for the advection. But certainly we need to come up with an alternative method for handling the sound and gravity modes. And I've just rewritten the table here in terms of Courant numbers now. So now if we fix the time step so that the Courant number associated with the horizontal motion is about 1, the Courant numbers that we're looking at for the vertical motions are up to 1,000 for sound and for gravity maybe, and up to 100 for vertical advection. So hopefully that kind of sets the scene for the problem. And so what we've started considering is using IMEX schemes, explicit schemes, but in an implementation whereby all of the horizontal terms are treated explicitly and all the vertically fast propagating modes, the acoustic and gravity modes, are treated implicitly. So this is this heavy implementation. And from here on in, I'm ignoring the problem of 3D advection because someone's telling me that they're going to treat it in a semi-Lagrangian fashion, so it's not my problem anymore. Thankfully. Okay, so I apologise for the titles on the last slide, so that's the end of my reference to fairy tales. Okay, so the framework that we're working in, I've just taken this linear equation set from a document that Andrew Staniforth put together early on in this work, so it could probably do with a bit of work still, but basically includes the processes that are deemed important for the atmosphere, but also in terms of their constraints on the stability of the system. So it includes advection, rotation, pressure gradient force, gravity, and thereby acoustic waves as well. And what I'm going to talk through is how we come up with an equation set that we're going to analyse for time stepping schemes, which is rather simpler than this. Sorry.
Between little u and big U?
Okay, so these are linear velocities.
Okay.
What's phi? What is phi?
Phi is effectively the pressure. P over rho.
What is the thermodynamic equation the effect of? Because it's usually the content pressure.
Yeah, it's a good question actually. Comes in here somewhere. I should have looked at this equation set more carefully.
There's
not another equation. You need one more equation.
Yeah. Okay, but assuming for a moment that this equation set looks okay, we can write it more simply in a kind of vector matrix form, where the frequency that's specified here, depending on how we define that, it will describe the terms that are included in this equation set. So if we wanted to consider a more simple form of the equation set that only included acoustic waves, for example, we would just reduce the expression for the dispersion relation effectively to only include acoustic terms. And to simplify that even further, we could then just consider this as a scalar equation, so just an oscillation equation. And so what we're trying to demonstrate here is that by considering an oscillation equation, it is analogous to a very simple form of the atmospheric equations.
Are there any gravity waves in your supernet system?
There are. This is meant to represent horizontally propagating gravity waves. So CG is the speed of gravity. As I say, I think
that's like a pressure equation. That would be like the sound wave speed times the divergence.
Yeah.
And there's no gravity in there.
As I say, I think this equation set is probably outdated. I think we could come up with something better, but I think the framework still works even if we rewrote the equations. So starting with a simple scalar oscillation equation, we can enhance the problem by identifying high frequency and low frequency terms, because we know we want to solve the high frequency terms with an implicit scheme and low frequency terms with an explicit scheme. And I'm going to denote them K sub H and K sub V to indicate what in our heavy scheme would be horizontally propagating modes and vertically propagating modes. So we know what the solution to the exact system is. We can derive an amplification factor from over a time delta t. And therefore, from that amplification factor, we know that its amplitude is exactly 1, and it has a phase that's described by the sum of those two frequencies. And furthermore, from the phase, we can define an expression for the group velocity. And these are the terms from the exact system that we're going to consider how the numerical scheme behaves against. This kind of scalar equation is going to be our initial analysis framework for a very simple system, and then I've extended the analysis to look at a 2D system describing horizontally and vertically propagating sound waves as well, which again could be written in a vector matrix form. We know what the analytical solution to that problem is. We can derive the dispersion relations. So we have 3 modes for this system, 2 that describe forward and backward propagating acoustic modes, and 1 which is a non-divergent, non-propagating mode in this case, because I have no linear advection in there. And therefore we can derive the amplification factor, which again has an amplitude of exactly 1 in all 3 modes, and we know what the phase is described by as well. So that's the exact system. And then when we come to look at the numerical system, the numerical scheme, again we can construct the amplification factor by looking at what the numerical scheme does from time step n to time step n plus 1, and construct the amplification factor, extract the numerical amplitude and phase from the expression for the amplification factor, and then that will give us an indication. I'm sorry if I'm rushing through this, but I think a lot of you know this very well, much better than I do, that if the amplitude is greater than 1, we have an amplifying and therefore unstable scheme. If it's less than 1, it's damping and stable. From the phase, we know whether the scheme is relatively accelerating or decelerating with respect to the exact system, and we can furthermore construct a numerical group velocity. And the reason we're interested in the group velocity as well is that Nigel and Andrew are particularly concerned about numerical schemes that cause waves to propagate in the wrong direction. And so we can consider whether the group velocities from the numerical scheme are actually propagating, even if they're not well resolved, or at least propagating in the right direction. And you can construct an equation that demonstrates that the group velocity from the exact system and effectively the gradient of the phase from the exact system with respect to that frequency should have the same sign. And the reason I've written it like this is because we're going to look at plots of phase against frequency, and so by eye we can just see from those plots whether the gradient has the right sign. It's a simple by eye check. And so for the comparisons, we're going to look at the performance of numerical schemes over small Courant numbers, so small Courant numbers for the horizontally propagating and vertically propagating modes. And for small Courant numbers, we would expect the scheme to provide stability, but also accuracy, i.e. not too damping, and good phase representation. We're also going to look over large Courant numbers, so out to vertically propagating Courant numbers associated with the vertically propagating modes of order 100. And over this range, we're obviously looking for stability still, and at this point, this is where we're just looking for good behaviour in terms of the group velocity. We're not expecting a good accuracy for large Courant numbers, but at least good behaviour.
Why do you care? Because basically what you got in there are the acoustic modes, and you know you're pretty much destroying them. So whether the group velocity is one way or another.
Yeah, Dale asked me this question last week when I was chatting to him, and I haven't got a good answer actually. And that's why I should quiz Andrew about it.
I think I can answer
Okay.
that. If the group velocity is the wrong way, then the material properties like energy and mass are propagated in the wrong direction, and that could lead to instability.
Well, stability is another issue, but and that depends on what that amplification factor is. We're just talking about the acoustic modes now, right?
No, but I think there is a more instability in this. If the property is transported in the wrong direction, you're getting a bad forecast.
You know, but the acoustic modes are supposed to be meteorologically insignificant.
Well, we're expecting to have vertically propagate the gravity terms in here as well.
You can still have a problem which you can easily see if you have a shallow water equation in one dimension with a mountain in it, and you average the solution in time for a very, very long time to get the stationary solution. You start running it, and if the group velocity is of this bad property, you still have some unstationary modes appearing.
But those are the gravity waves, aren't they?
Yes, these are gravity waves. But of course, this effect disappears if you put in a little bit of diffusion, which kills these waves because they are, these high order schemes, very much concentrated near to delta x. So they can easily be trapped, but if they are not trapped, so in one dimension you can run without diffusion, you see them popping up all the time, even though you think we have a stationary solution. It doesn't remain stationary. Then imagine you have not a shallow water equation, but something like heat generation out of a divergence field with moisture. Then, of course, it can be a problem. But this problem is easily caught by a proper amount of filtering.
But I think that one of the philosophies that it's better to not have the problem rather than trying to fix it afterwards.
Yeah, I think this is where Nigel and Andrew are coming from. Absolutely, that's definitely their philosophy. Okay, so finally, the other thing we're going to consider is from the Met Office's perspective, they would like some sort of fair comparison of an explicit-based scheme compared to their current semi-implicit scheme. So I can't remember whether I pointed it out now. I think I did when I was giving a summary of the current global model, that they currently get away with a time step which is about 10 times longer than that which you might associate with resolving horizontally propagating modes. And so therefore, what we also will look at is the accumulated error over 10 time steps from the heavy scheme, the IMEX scheme, compared to a single time step from the from a implicit scheme. And if you accumulate errors over 10, in this case 10 steps, the amplification factor from, or the amplitude from the amplification factor for an implicit scheme from a single time step would compare to the amplification from the heavy scheme to the power m, and the phase is multiplied by this number m, the number of steps. So that's a further comparison we'll do in these analyses. Sorry, I'm running out of time fast. So we've limited our analyses to Runge-Kutta IMEX schemes. This is just a summary of what Runge-Kutta IMEX schemes look like in general, and I'll not talk through that greatly, but the reason we've limited our our considerations to RK schemes for the moment is that they don't have an inherent computational mode, and Nigel particularly seems very wary of computational modes, so we're sticking to RK IMEX schemes. Okay, so
is that every RK scheme or just the family you're considering?
Do or don't, as in don't have
Yeah.
computational modes. I think by definition they don't have a computational mode because they're only integrating over a single time level.
I think the question was whether you take Runge-Kutta 2, 3, or 4.
We've looked
I have
at
a selection of that.
We've looked at a range of schemes.
And
I'll show you a few results in a minute. So the way that we're performing this analysis for the 2D acoustic system that I described earlier, an RK IMEX scheme in general looks like this. So we have intermediate stages, predictor stages, and what I've done here is apply the explicit scheme to the horizontally propagating mode and the implicit scheme to the vertically propagating mode, and then you kind of clean up the scheme with a final stage which sums up those predictor stages. And from that you can define a set of amplification factors which gives you the final amplification factor for the scheme. Again, I'm not going to talk through that in any more detail. I wrote this slide for a meeting at the Gung Ho group a while back and wrote it very late and was getting very tired by this stage and found myself asking where have we got to, which is almost a favourite line in our house at the moment. So what have we got? It comes from 1 Newton a Suit, one of my son's favourite books. And what we have got is a method for generating the amplification factor for a general RK IMEX scheme, so we can just kind of plug in an RK IMEX scheme for this particular system of horizontally and vertically propagating modes, and bring out the amplification factors. And just to note, because this is a system with 3 variables, this amplification factor is actually a 3x3 matrix, and therefore we're considering stability and accuracy properties for the scheme in terms of the 3 eigenvalues of that amplification matrix. Okay, so starting with the simple system, the generic wave equations, the generic scalar wave equation, we've considered a number of schemes. I'm not going to go into much detail at all, but we've looked at first of all just an implicit scheme applied to all the terms, which is off-centered trapezoidal, and we're using this as the kind of benchmark scheme. So this is meant to be analogous to what the UM currently does in their semi-implicit schemes. This is kind of what we're trying to beat, I guess. And then we've looked at various combinations of third-order Runge-Kutta with trapezoidal scheme, and this includes the so-called strand carryover scheme, which is described in Ulrich and Jablanowski. We've also looked at multiple iterations of second-order Runge-Kutta with trapezoidal, and these are based on formulations that are used in the Met Office's latest forecasting model, Endgame. And we've looked at schemes from the literature, including so-called strong stability-preserving schemes, so from Pareschi and Rousseau and Asher et al. Our benchmark scheme, the off-centered trapezoidal, looks like this. And we've considered the case with just small off-centering of 0.1, so this is equivalent to what's being done in the UM's, the Met Office's latest endgame model. And from that we construct the amplitudes, which are always stable but damping, and phase, which is always decelerating. I'm flashing up some figures here because I'm going to show you some more figures, so hopefully this helps you get your eye in. So rather than just looking at the equation descriptions of those characteristics, what I've tried to plot here are first of all amplitudes for small courant numbers. So along the bottom here you've got courant numbers associated with the horizontally propagating modes going from -2.5 to +2.5, and up the vertical axis courant numbers associated with the vertically propagating modes from -2.5 to +2.5. And so for the off-centered trapezoidal, the minimum amplitude, so the amplitudes go from neutral, where you're along the diagonal axis, and then kind of rapidly damping as you get to larger courant numbers. and for large current numbers, so now ranging from 0 up to 100, we see that the minimum amplitude soon reaches 0.8, which is basically the maximum damping you get from the scheme. On the right-hand side here, I've got plots of the phase. This plot here is meant to indicate what the exact phase is doing for this scalar equation, scalar wave equation, and what I've got here in colours are the values of the phase from -pi in dark blue to +pi in red. And so what this is indicating is just that as the current numbers range over these numbers, the amplification factor is simply rotating around the unit circle, as we all know. And a similar plot for the off-centre trapezoidal, we can see that those contours are spreading out, which indicates the deceleration which we saw from the analysis. And so what I'm again trying to indicate here is that this idea of by eye, we can see that the gradients associated with this phase are in the same direction from the numerical scheme compared to the exact scheme. So the group velocities are well behaved, and if we look over large current numbers from 0 up to 100, the phase kind of comes to a halt, but it doesn't start showing signs of the group velocity acting in the wrong direction. So in terms of IMEX schemes, we've looked at a number. The one that we've taken from the recent literature, the strand carryover scheme from Ulrich and Jablanowski, I've presented here. And the amplitudes are very well behaved, so they basically have no dependence on the implicit part of the scheme. So the stability is just that associated with straightforward three-stage RK3. From the phase, here we've got the exact system, the off-centered trapezoidal, and the phase from strand carryover, which you can see gives a much better representation of phase compared to the exact system than does the off-centered trapezoidal. Another big advantage of this scheme is that it has a single implicit solve over the whole time step. So it looks to be showing good accuracy, good stability, and it's cheap. By comparison, just picking one of these strong stability preserving schemes from the literature from Peresci and Russo, despite the name, applied to this generic wave equation, we actually see some rather alarming stability properties. So instabilities extending right across the current number range, even to very small horizontal current numbers, and strong damping even for quite small current numbers. So from this analysis, it kind of suggests that we might be wary of such schemes. And in addition, this scheme has 4 implicit solves per time step, so it's expensive as well. And now I'm going to...
That's not the kind of stability... There's strong stability preserving, it's not the kind of stability you're assessing, right?
Sure, yeah. So again, whizzing through this, for the 2D acoustic wave system, I've plotted here what the phase looks like from the exact system. So this is horizontally propagating current numbers, -2.5 to +2.5, vertically propagating current numbers, -2.5 to +2.5, and now we've got 2 eigenvalues representing the forward and backward propagating acoustic modes. And again, I've just kind of extended the range of current numbers over which we look, and the pattern just repeats over and over again. It's what we would expect. But what happens from the numerical schemes? So
the 2D acoustic waves are ones with total wave number that's constant in the ring. Because you were really looking at 2D acoustic waves before, right?
Yeah.
The previous set of plots had specific values of essentially horizontal and vertical wave number, but you take out the speed of sound scaling.
Yeah.
So this is just stuff that's symmetric in that's circularly symmetric acoustic waves. Is that what we're looking at?
Well, the system is, the 2 systems are different. So the simplified system is a single scalar equation, whereas now we're looking at this three variable coupled system. So we're now having to extract 3 eigenvalues from a 3x3 amplification matrix, and we're looking at the 2 eigenvalues that represent the non-stationary modes. And so got the system plotted at the top. If we look at the strand carryover, what I've plotted now is the maximum amplitudes from the amplification factors, which is what's going to indicate stability. And so again, we see good stability properties. So there's very little dependence on the vertical current number in terms of stability, and the phase representation that's good for small current numbers. Over these large vertical current number ranges, again, the stability continues to look good, and as expected, the phase kind of just stagnates after a short while. And at the bottom here, I've got the plots of these accumulated amplitudes and phase. So this is now looking at time steps associated with the pure implicit scheme from -2.5 to +2.5. But in order to get to that time, I've taken 10 repeated integrations from the heavy scheme. And so over a time step where you would hope to get good representation from the current semi-implicit implementation, the accumulated amplification from the Runge-Kutta IMEX scheme is showing excellent amplitude properties and very good phase representation up to really quite large current numbers, which, I mean, this is news to the Met Office. I don't know whether it's news to anyone else, but it was news to the Met Office. They're not so familiar with the properties of repeated short steps from explicit-based schemes. Tell me when to stop. Someone kick me off when you're sick of listening to me. So this this is based on the kind of a first attempt of building a heavy scheme from this Runge-Kutta IMEX approach. So everything that's horizontally propagating is being solved with the explicit scheme, and everything vertically propagating is being solved with the implicit scheme. Now Hilary's started doing some numerical experiments with these schemes, and when she started coding them up, it occurred to her that a more sensible coding approach is to use something like a forward-backward scheme for the implicit parts, for the acoustic terms at least, because in updating the U solution, you now have in updating the pressure solution, you already have a new U solution, so why not use that new U solution? And so what she's done is used the implicit scheme to define how to use that latest U solution. So it's not really an extra implicit step. You already have the information, but you're using it in the way that the implicit scheme in the Runge-Kutta IMEX scheme defines. So this analysis on this page is what we've called U forward, P forward. So just a kind of the most obvious on paper heavy implementation for an Runge-Kutta IMEX scheme. By contrast, if we shift the term that uses the new U solution for the new pressure solution into the implicit scheme, and we call this U forward, P backward. So it's analogous to the forward backward scheme that's used in split explicit schemes. We get quite different properties. So first of all, we get completely neutral stability within the stable range. The phase representation probably doesn't differ greatly. But the stability is really enhanced by this simple change.
Can you retain the order of the base method when you do that change?
Yeah, I think so. I think Hilary will show those results on Wednesday when she talks, actually. Yeah. However, it's the results from doing this U forward, P forward, or U forward, P backward aren't universal across different schemes. So here I've looked at the higher order Runge-Kutta IMEX scheme that I considered against the scalar equation earlier. These are very preliminary results, so I've just kind of put that across there just to be sure that's clear. But in this forward approach, we get more limited stability than we saw from the strand carryover scheme. Reasonable representation of the phase for small current numbers, but we can see that there's this kind of region for larger current numbers, larger vertical current numbers, where the stability actually reduces in this form. If we then implement the scheme in this forward-backward approach, again the results change. We've got enhanced stability again for small current numbers, and it cleans up the instability at slightly larger current numbers in the vertical direction. and still retains good phase representation. However, we have looked at other schemes where moving to this forward-backward approach doesn't have the same result. It doesn't always produce extra stability, so it's a case of having to look at these analyses scheme by scheme really to see the effects. But the other thing to note here is that this much higher order scheme is giving much more damping than the strand carryover scheme. So to finish, this is work in progress. I've got further analyses to complete for different schemes, so I'll have hopefully some firmer conclusions soon. But as a preliminary comment, I would say that the strand carryover scheme that's being used that was described in Ulrich and Jablonowski certainly appears to have a really good combination of characteristics. It's accurate, very stable, and it's fast. It has one implicit solve per time step compared to much more expensive RK IMEX schemes that we've looked at. Okay, thank you very much for listening.
Have you considered the additive RK methods of Kennedy and Carpenter?
No, I don't.
I think they're kind of like the gold standard.
Okay.
So I recommend.
Okay.
It'd be interesting to see the analysis that you've done
Yeah.
with those methods.
Yeah.
They have a whole family of methods from order 2 to 5.
Right. Okay. Yeah. Now I've got the reference of you later.
So I think it's tricky to interpret the group velocities for your first fast wave, slow wave ODE,
Okay.
because there's no real group velocities in ODEs. You have to have an XT dependence, and it's all relevant, but I just think it's going to be a little complicated thinking about how they all go together. In particular, kind of related to some of the earlier comments, we don't really care that much about the sound waves, and then we start to have certain terms that are treated implicitly and explicitly in some other modes, like the gravity waves or the velocity waves or something.
Yeah.
It gets, the behaviors can be very different, so I'm sure you're aware of that. But nevertheless, as you start to split up a more complicated equation with two actual different real wave modes,
Yeah.
things could be a little different.
Okay.
Is the number of implicit solves relevant, or I don't think it would be, even if it's only 1D?
Yeah, I mean, I would say I think that's why strand carryover looks like a good candidate for now, because if you can get good results from a scheme that only has one implicit solve, even albeit a 1D implicit solve, it's got to be cheaper than having to do 4, for example.
But isn't the answer different? Isn't the answer to John's question no? As long as it's 1D, it's just order a number of good points. So the implicit solves aren't that expensive.
No, but
Not so.
in the future, it could be still very large number of grid points.
In the vertical.
For what, 100? 100 by 100?
We're not talking about being outside we're not talking about being outside a uniform memory region on one of those solves. So therefore, we probably don't care.
It just scales its order number of points. This is
And it's a tri-diagonal or maybe 5-diagonal if you have a big extensor system. So it's a very well-behaved system from that perspective. So I wouldn't be very scared about that system on any hardware we're going to hit, anytime in the foreseeable future.
Just no more, like the cost of a derivative or something.
I have a question. As far as I could follow, you have on the high order Runge-Kutta IMEX, only the Runge-Kutta 3. All the others, you seem to tend more to the low order one, and what bothers me that you didn't take the classical fourth order. I mean, there was a time when everybody knew only the fourth order. And it has quite nice property because the Courant number is 2.8, which is really interesting. Yeah. So why did you not consider that more?
I can't remember off the top of my head whether we have looked at any IMEX schemes that include RK4. We haven't ruled it out completely. And we certainly, when I started looking at this, I started with a very, very basic analysis and did look at RK4, and Mikhail Baldav has kind of suggested RK4 in his latest analysis for that very reason. Yeah, I'd have to look back at. I can't remember whether any of the schemes we've actually ended up going through from the literature go as far as 4 stages of the explicit scheme.
Yeah, so one of the Kennedy and Carpenter
Mhm.
method is the RK4.
Okay,
It's an implicit RK4 with an explicit part.
right.
That is not exactly the classical RK method, it's close.
Yeah, yeah. I think actually thinking about it, one thing that's, again, this is not to say that it should be ruled out for this reason, but one thing that I remember from looking at RK4 in the simplest sense was that you're right, you get a much longer time step, but it's very damping within that stable region. So much more damping than RK3, and so over the time step that you might achieve from RK3, you wouldn't actually want to go further than that time step with RK4 to still get good solutions. So it's a very damping method once you get out to those long time steps. So,
But the damping is concentrated on the relative fast phase, is it?
Yes,
yeah.
but it depends on whether you want to damp those waves or not. If you care about those waves, you can't take that time step. If you want to damp them, it's a perfect scheme.
Thanks very much.
Thank you.